Okay. Welcome, everybody. It's a great pleasure to me to introduce Francesco Pediconi. He is from Università di Firenze. And today he is going to speak about Uncomogeneity-one Hermitian non-Kähler methods. Thank you, Francesco.
Okay, so first of all, I would like to thank Romina and the organizers of these seminars for giving me the opportunity to speak here today. So today, my talk will focus on cohomogeneity-one Hermitian manifolds, and especially on the non-Kähler setting. Okay, so let's start with some background. So in general, you know that in differential geometry, we use Lie group actions in order to simplify the study of geometric problems. Okay, so for example, one famous problem in Riemannian geometry is the finding of Einstein matrix. So let me recall that an Einstein matrix is a metric whose Ricci tensor is proportional to the metric itself. Okay, so that Ricci is equal to lambda g for some lambda in positive some lambda constant. So in general, this is a nonlinear system of PDEs, so it is really hard to solve, to handle with. But actually, so you can use Lie group methods in order to simplify the study of this problem. So if you assume that the existence of a closed subgroup of isometries of the manifolds that acts transitively on the manifold itself, then what happens is that you can actually present your manifolds as a quotient G over H, where H is some compact subgroup of G, okay? And in this situation, any G invariant tensor field on your manifold is uniquely determined by its value at your favorite point, P, okay? And in particular, it follows that the Einstein equations reduce to a set of algebraic equations, which, I mean, in general, are still very difficult to handle with, but they are definitely easier than the general case, okay? So this is like one powerful tool in order to study Einstein metrics. Another powerful tool for studying Einstein metrics comes from the complex geometry, and it is the so-called Aubin-Calabi-Yau theorem. So it tells you that if you start with a compact complex manifold which admit Kähler metrics, okay, then if the first Chern class of the manifold is negative or it is zero, then in this case, you know that there exists at least one Kähler-Einstein metric on your manifold. Okay, this is like a very powerful theorem in complex geometry, and it was conjectured by Calabi in the 50s, and but actually this is just an existence result. Okay, so this is not constructive in the sense that it tells you that, okay, so you can find these nice metrics on the manifold, but you don't know how they look like or how they can be constructed. And also another remark which is worth mentioning is that the case of positive first Chern class is obstructed. So in general, you don't have the existence of Kähler-Einstein metrics in the positive, in those compact Kählerian manifolds which have positive first Chern class, okay? There are some obstructions. And so it is not easy to find Kähler-Einstein metrics with positive scalar curvature. So actually, historically, the first non-homogeneous example of a compact manifold admitting an Einstein matrix with positive scalar curvature has been provided by Page. And he constructed this metric, which is a cohomogeneity-one metric, on the blow-up of CP2 at one point, which is basically the connected sum of CP2 with another copy of CP2 with the opposite orientation. Okay? So this metric constructed by Page, it is an Hermitian metric. So it is Einstein metric, it is Hermitian, but actually it is non-Kähler. So in principle, one can ask whether the blow-up of CP2 admits a Kähler-Einstein metric. So the answer is that even though this manifold admits Kähler metrics, it does not admit any Kähler-Einstein metric. And the reason for that is that, as I said before, in general, there are obstructions to the existence of Kähler-Einstein metric in the positive first-rank class case. And one of the obstructions is that the automorphisms group of the manifold, okay, which is a Lie group, has to be reductive. And in this case, it is well known that the automorphisms group of this manifold is not reductive. And so in the end, you can say that this manifold surely does not admit any Kähler-Einstein metric, okay? So,
Francesco?
Yeah?
What about just Einstein metrics?
Yeah, the Page metric is Einstein.
Ah, sorry. Yeah.
It is Einstein, it's Hermitian, but non-Kähler.
Okay, sorry, yes.
So, this metric, of course, is Einstein metric, so it's really nice in order to understand the Riemannian geometry of the manifold. But from a complex viewpoint, I mean, this in principle can be not optimal, right? Because in the non-Kähler case, the Levi-Civita connection does not preserve the complex structure. And basically, this means that it does not give you lots of information about the complex geometry of the manifolds. So the idea is to look for other conditions which are like the analog of the Einstein matrix in Riemannian geometry in this non-Kähler Hermitian setting. One of these conditions is the so-called Second-Chern-Einstein condition. So I will tell you during the talk precisely what does it mean. So the question is, there exists these other kinds of special metrics on this manifold, which maybe are better from the complex viewpoint. Well, the answer here is no. And we know that the answer is no by means of the following theorem, which have been proved by Goduchon and Ivanov. So in particular, they prove that if X is a compact complex manifold of complex dimension 2, so it is a complex surface, then X admits a Second-Chern-Einstein metric if and only if one of the two following conditions is satisfied. So either X admits Kähler-Einstein metrics, or X is the op surface. So as you can see here, you have, so basically the existence of this special kind of matrix is related to the existence of Kähler-Einstein metrics, with the only exception of the op surface. So in general, at least in complex dimension 2, you have no chance to get all the special metrics which are not Kähler-Einstein, okay? But the point here is that the Goduchon-Ivanov theorem just holds true in complex dimension 2. So the starting point of our work is that, okay, so maybe there's the chance to get special complex metrics, special Hermitian metrics in higher dimensional manifolds by using a cohomogeneity-one approach. Okay, so let's have a look at let's have a better look at this Chern-Einstein condition. So let's take an Hermitian manifold X. Okay, so attached to this manifold, you have the Levi-Civita connection and the fundamental two form omega given by G and J. Okay, so as I said before, the Levi-Civita connection in general is not complex. So in general, it does not preserve the complex structure of the manifold. So it is very, very useful here to consider other linear connection on the manifold, okay, connections which preserve both G and J. Among these complex and metric connections, maybe the most famous one is the so-called Chern connection, which is given by the formula here in the slide. Okay, so basically you are taking the Levi-Civita connection and you are adding some term, which is given by the d omega. So this new connection that you obtain with this formula, it preserves both the structure, so G and J, and of course, in general, it has torsion. So you pay a price here. And the torsion is given by, basically by d omega, okay? So by these formulas, it follows immediately that if the metric G is scalar, then this Chern connection, actually, it is equal to the Levi-Civita connection. But in general, for non-Kähler metrics, they are two different connections. Well, of course, since it is a linear connection, you can consider the curvature of this connection that we called Chern curvature, okay? And since this connection has torsion as a torsion part, which is non-zero, it does not satisfy the usual symmetries of the Riemannian curvature tensor, okay? So in particular, one implication of this fact is that there is not just a way to trace the Ricci tensor out of this curvature. There are at least two ways to trace the Ricci. And so we define the first Chern-Ricci tensor of the manifold to be the trace of the curvature tensor by means of, so here you take the trace on the second two indices, okay? So basically you are tracing the endomorphism part of the curvature. The other Ricci tensor that you can get, which is the so-called second Chern-Ricci tensor, is taken by consider the trace of the curvature by means of the first two indices, okay? So in general, these two objects that you define in this way are different. They are not the same for general non-Kähler metrics. And I say that there are at least two ways, because in principle, you can trace the Ricci in other ways, so giving rise to other tensors. But at least, so as far as I know, the only two geometric relevant objects are these two. So let's say that the important objects are these two Chern-Ricci tensors. Moreover, as in the Riemannian case, you can trace again the curvature in order to obtain the analog of the scalar curvature, that in this case we call Chern scalar curvature, which basically is the trace of both the Ricci tensor. So if you take the trace of the first Chern-Ricci tensor, this is equal to the trace of the second Ricci tensor, and this trace, it is called this Chern scalar curvature. And it is just a smooth function on the manifold itself. So since we have these two analog, the complex analog of the Ricci tensor, we can consider the analog of the Einstein condition in this context, okay? So here we say that an Hermitian manifold is first Chern-Einstein, is the first Chern-Ricci tensor is proportional to the metric G. And we say that the metric is second Chern-Einstein if the second Chern-Ricci tensor is proportional to the metric G. So here, let me stress this fact that this is the big difference between the Hermitian non-Kähler setting and the Riemannian setting, is that when you define the Einstein condition for Riemannian metrics, then if the Ricci tensor, if the Riemannian Ricci tensor is proportional to the metric, then the proportional factor is necessarily constant, at least in dimension greater or equal than 3. So here for a Hermitian manifold, this is not the case anymore. And in general, you can have that this lambda here, which is the Einstein factor, is a function, it's a not constant function. So this is why we introduced this nomenclature that we called strongly Chern-Einstein if the scalar is lambda, which is equal to the scalar curvature, is constant. Otherwise, we say that the Chern-Einstein metric is weakly Chern-Einstein. Okay.
So you don't have the Bianchi identity.
Yeah, I mean, you have the Bianchi identity, but you have the Bianchi identity with torsion.
Okay.
Yeah, so it is not the Bianchi identity of the Levi-Civita connection.
Okay.
So that's the issue. Yeah.
Thanks.
So basically, we have these two notions of special metrics in complex geometry, but we are mainly interested in just the second one, and that's the reason. So the point is that basically compact first Chern-Einstein manifolds are understood in this sense. So if you take a metric G, which is first Chern-Einstein on a compact complex manifold, then you look at the Chern scalar curvature, and if the Chern scalar curvature lambda is not constantly zero, then it has been proved by Angela, Calamai, and Spotted that actually G is globally conformal to a Kähler-Einstein metric. Okay, so in the conformal class of G, you can find a Kähler-Einstein metric, which in principle is much better than just being first Chern-Einstein. Okay, so in the other case, when the Chern scalar curvature is constantly zero, then in this case you have that the first Botchan class of the manifold is necessarily zero, and the manifold X in this case is called Calabi-Yau in the Kählerian setting, or non-Kähler Calabi-Yau in the non-Kählerian setting. So it depends whether the manifolds admit Kähler metrics or not. So in the Kählerian setting, you have the Calabi-Yau theorem, while in the non-Kähler setting, well, these manifolds have been studied by Tosatti, Venkov, and other people, so they are basically understood. On the other hand, the second Chern-Einstein metrics are in some sense more promising, and they are related to another notion which appeared in the literature called Hermite-Einstein condition. So in general, when you have an Hermitian vector bundle over a complex manifold, okay, you can take the curvature of the Hermitian vector bundle and you can contract it by means of the metric on the manifold, okay, and you say that this Hermitian vector bundle is Hermite-Einstein if this contraction of the curvature is proportional to is an endomorphism which is proportional to the identity. So basically, this condition is very similar to the second Chern-Einstein condition, because if you take an Hermitian metric, okay, of course, it induces an Hermitian metric on the holomorphic tangent bundle, and this Hermitian metric on the holomorphic tangent bundle is Hermite-Einstein with respect to itself, if and only if the metric that you started with is second Chern-Einstein with respect to the definition that we gave above. So there's this way to interpret this condition in terms of Hermite-Einstein condition. And in general, the point is that we don't have many examples of this kind of metrics. Okay, so up to my knowledge, the only examples that we know of second Chern-Einstein manifolds are these ones. So of course you have that all Kähler-Einstein manifolds in particular are strongly second Chern-Einstein, okay? Because for Kähler manifolds, as I said before, the Chern connection is equal to the Levi-Civita connection, so the two conditions agree. Other examples are given by the holomorphically parallelizable manifolds, which are basically the complex Lie groups and their quotients, and they they admit strongly second-Chern-Einstein metrics because they admit Chern-flat metrics. So these metrics are trivially both strongly first-Chern-Einstein and strongly second-Chern-Einstein. Okay. So another example is given by the linear Hopf manifold. So the standard metric on the linear Hopf manifold is strongly for second-Chern-Einstein. And other examples have been constructed by Podesta in 2018, which on compact homogeneous spaces, and by Angela Calamai and Spotti on 4-dimensional solvable Lie groups. So as you can see, all of the non-trivial examples of these special kind of metrics are very recent. So in general, we would like to obtain more examples, and that's why we decided to use the cohomogeneity-one approach in order to investigate whether you can obtain non-homogeneous examples with this approach. So let's have a look at the cohomogeneity-one setting. So here in this talk, we will focus mainly on the so-called standard cohomogeneity-one Hermitian manifolds, which are like a special class of these manifolds, which are constructed as follows. So you take a complete Hermitian manifold, okay, and you assume that there exists a semi-simple compact connected real Lie group G, which acts on the manifold X by means of holomorphic isometries, okay? And you also assume that this group have principal orbits of codimension 1, okay? So if you look at the orbit space, so the quotient G of X mod G, then this orbit space I is necessarily one of the following 4 possibilities. So if the manifold is non-compact, then the orbit space can be either R or the half line 0 plus infinity. So in the first case, you have no singular orbits, so all the orbits are principal, while in the second case, you have one singular orbit which corresponds to the boundary point 0 of the interval. On the other hand, in the compact case, okay, the orbit space can be either the circle or the closed interval 0 pi. So in the first case of the circle, again, all the orbits, it means that all the orbits are principal, while in the second case, you have precisely 2 singular orbits, which corresponds to the boundary values 0 and pi. Okay, so of course here you can fix the value pi by allowing rescaling, but you can also, I mean, it is not really important that the precise value is pi. So in all of these 4 cases, you can always choose to fix a unit speed geodesic which intersects each orbit orthogonally. Okay, and so and you can choose and you can use these geodesics in order to parameterize the regular part of the manifolds, where the regular part is the union of the principal orbits. So we put some hypotheses on these manifolds in order to simplify the study of them. Okay, so all the principal orbits here, which corresponds to the internal values of R in the interval, are equivalently isometric to a fixed homogeneous CR space G over H. Okay, with a family of adaptive invariant metrics. So here, basically, what I'm saying is that the principal orbits cannot be complex because they are odd-dimensional, but they inherit a CR structure. Okay, and we are assuming that this CR structure is constant along the geodesic. Okay, so it does not depend on R. And the family GR of invariant metrics are induced by simply by restricting G to the principal orbits. Moreover, we also assume that the normalizer of the connected components of H inside G centralize a torus, and that the dimension of this group K is precisely equal to the dimension of H plus 1. So here we are saying that the trivial summand of the isotropy representation of the homogeneous space G over H is just one-dimensional, okay? So we also assume that so in order to be standard, that the singular orbits, okay, which corresponds to the value of the boundary of the interval, are generalized flag manifolds with the induced Hermitian structure. So here, what I'm saying is that if there exist singular orbits, then these singular orbits are generalized flag manifolds, G over L, and this Lie group and these Lie groups L verify the following conditions. So so you have this inclusion of Lie groups. So H is containing K, which is the normalizer of the connected components, which is contained in the intersection between of L minus with L plus. So here L minus and L plus is in the case of two singular orbits. So for example, in the case of just one singular orbit, you just have one Lie group L, okay? And the quotient of L over H are spheres. Okay, so this is the general picture of how a standard cohomogeneity-one Hermitian manifold look like. The easiest example that you can think is the manifold that we saw at the beginning of the talk, which is the blow up of CP2 at one point. So basically, this manifold is constructed in this way. So you take CP2 and you take the action of the Lie group SU2 on CP2, which fix a point, okay? So you remove that point and you glue another copy of CP2 with the opposite orientations. And what you get is a well-defined action of SU2 on the blow up of CP2. So here, with respect to this action, the singular orbits are isometric to CP1, okay, and the principal orbits are isometric to the free sphere S3. Okay, so here this corresponds to the last case, so where the manifold is compact and you have two singular orbits. So one special kind of such manifolds have been studied by Berard Bergery in a famous work when he constructed some example. So he basically he generalized the page construction and he constructed some examples of inhomogeneous Einstein metrics on cohomogeneity-one spaces. Okay. So in some special class of standard cohomogeneity-one Hermitian manifolds. So let's have a look at how they are constructed. So these Berard Bergery manifolds are constructed in the following way. So you start with a simply connected, irreducible, compact Hermitian symmetric space P equal to G over K. Okay. You assume that the complex dimension of P is equal to M minus 1, okay? And attached to this space, you consider this number P, which is the unique positive integer, such that P minus 1 times the first chain class of P is an indivisible integer cohomology class of P. Okay, so these spaces are classified, so you can find them on the best book, for example, and basically you have 4 families, which depends on some parameters, okay, together with 2 exceptional examples given by the exceptional Lie groups E6 and E7. Okay, so here you find all the possibilities for P and the corresponding values of M and P. Okay. So once you have this manifold, it is well known that the center of the isotropy K is a circle, okay? And so this gives rise to a family of homogeneous circle bundles, okay? Sigma n over P, where this n is actually a twisting factor. So for any n, you can define an homogeneous circle bundle in this way. So by taking H to be the semi-simple part of the isotropy, and sigma n to be like G over H times the n. Okay, and of course, since G is compact, you can always fix a beam variant Riemannian metric on G, and this gives rise to an orthogonal splitting of the Lie algebra G, okay, into three parts: H plus A plus P, where H is the semi-simple part of the Lie algebra K. A is the center of K, and it is tangent to the vertical, to the fiber of the circle bundles above, okay? And P is the complement, which is tangent to the manifold P, to the base space of the circle bundle. Moreover, you can always rescale the metric Q in order to obtain that the restriction of Q to the base is the Kähler-Einstein metric on P with Einstein factor 2m. So basically, for example, if you decide to start with P equal to the complex projective space, okay, then what you get is that the homogeneous circle bundle is nothing but the op fibration, okay, and the Kähler-Einstein metric on the base is nothing but the Fubini-Studi metric with sectional curvature between 1 and 4. So this is like maybe the most easy case that you can consider with this construction. So, well, once you have these homogeneous circle bundles, okay, you can build cohomogeneity-one, standard cohomogeneity-one Hermitian manifolds by taking associate bundles to these homogeneous circle bundles. So you have four possibilities, okay. So the easiest case is that you just take sigma n cross R, okay. So in this case, you get a cohomogeneity-one manifolds with respect to the action of G, and here the orbit space is the straight line R. Another case is that you can take the associate bundle to sigma n by means of the standard action of the circle on the complex plane. Okay, so here what you get is a non-compact space. Is a non-compact space with one singular orbit. The third one is nothing but the product of sigma n cross the circle, while the last one is the associate bundle of sigma n by means of the standard action of the circle on CP1. Okay. So just to give some concrete example of what you can get by means of this construction. So if you start with the op fibration over the complex projective space, then the four spaces you get are the following. So you get the product of the odd sphere cross R in the first case, or you get the tautological line bundle over the projective space in the second case. So in the third case, you just get the linear op manifold, so the odd sphere cross S1. While in the last case, you get the connected subom CPM with another copy of CPM with opposite directions, which is the higher dimensional analog of the page manifold. Okay, so now that we have these manifolds constructed by following Berard Bergery, the point is that we can that we can describe invariant metrics on such manifolds in an easy way. So of course, the regular, so we can always any metric, okay, any invariant metric on these manifolds are completely determined by the restriction on the regular part of the manifold, where the regular part of the manifold again is the union of all the principal orbits, okay. And in the regular part of the manifold, any invariant metric which is of summation type with respect to the fibration x over p takes this form. Okay, so it is basically given by two functions, f and h, where f is the length of the S1 fiber of the fibration of sigma n over p, while h is just a scale factor over the base p. So here, let me stress that by means of summation type, I mean that these metrics are invariant by means of the action of G, and they induces a metric on the base space of P, which turn this fibration into a Riemannian summation. Okay, so these conditions told us that basically you just need two functions in order to describe these metrics. Okay, so there are questions up to now, or is it clear? Okay, so let's move on. So once that we have these metrics, so the aim is to try to characterize which of these metrics are special, in the sense that if there are some special metrics of this kind, okay, so that they verify some special conditions. And we begin by look at the local conformally Kähler condition. So the first theorem that we prove together with Daniele Angella, which is my supervisor during this postdoc in Florence, is that if you take, so in this setting, so if you take a Berard Bergery manifold together with a metric constructed in that way, so that it depends only on two functions, then any of this metric is locally conformally Kähler. Furthermore, if you ask that this metric is strictly locally conformally Kähler, then it follows that all the orbits of X are necessary principal, and in this case, G is Weissman if and only if the metric is homogeneous. So let me say something about these conditions. So,
Francesco, are there Einstein metrics among these metrics?
Berard Bergery constructed real Einstein metrics by means of this construction.
Okay, so that's solving an ODE on the functions.
Yeah, exactly. Yeah, exactly.
Okay, so but for any space there is an Einstein, at least one.
I think that no. It depends on the family. So in the Riemannian case, it depends on the family. So for example, in the compact case with two singular orbits, you have the existence of Einstein metrics for special value of n. So n is the twisting value of the homogeneous circle bundle, and you have the existence of Einstein metrics when n is between 1 and p, where p is that cohomological value given by the first chain class.
Okay, thank you.
Okay, so it is not always the case that you can find Einstein metrics. So going back to this to this theorem, so we studied the locally conformally Kähler condition, and let me recall that a metric is locally conformally Kähler if locally it admits conformal change to a local Kähler metric. Okay, So this condition can be rephrased also in this way. So if you consider omega to be the fundamental true form of the given by G and J, and theta given by to be the trace of the torsion of the Chern connection of the manifold, which is called the Lie form, then G is locally conformally Kähler if and only if d omega is equal to 1 over m minus 1 theta wedge omega, and theta is closed. Okay, so you can characterize this condition of being locally conformally Kähler by means of this algebraic condition. And a metric which is locally conformally Kähler is said to be strictly locally conformally Kähler when the metric is not globally conformally Kähler. Okay, so being strictly locally conformally Kähler is equivalent to ask that the Lie form, which is closed, is non-exact. Okay, so and in this case, if the metric is strictly locally conformally Kähler, it is Weissman if and only if the Lie form, which is the trace of the torsion, is parallel with respect to the Levi-Civita connection. Okay, so in this setting, all of the metrics are locally conformally Kähler, and moreover, strictly Weissman metrics appear just in those manifold which doesn't have singular orbits. Is it worth mentioning that by this theorem it follows that there exist compact manifolds which admits cohomogeneity-one strictly locally conformally Kähler which metrics which are not Weissman. And this is worth mentioning because actually in the homogeneous case, this is not possible because it has been proved by Goduchon, Moroiano, and Ornea in 2015 that any metric which is homogeneous and strictly locally conformally Kähler on compact manifolds are necessarily Weissman. So here it is like the first difference between the cohomogeneity-one setting and the homogeneous setting. So the other theory.
But Francesco, if all the orbits are principal, then you never get compact, right? For the total space.
No, that's not true because, for example, in the Hopf manifold, it is compact and all the orbits are principal. So if you take just the product with S1.
Oh, okay.
Yeah. In that case, all the orbits are principal, and in fact, the standard metric on the Hopf manifold is Weissman. So this can be seen like a generalization of this result, if you want. So another result in the direction of characterizing special metrics on these spaces is the following. So in this setting, okay, of metrics on these Berard Bergery manifolds, the following three conditions are equivalent. So G is pluriclosed if and only if G is balanced, if and only if G is Kähler. Okay. Moreover, if the manifold X has singular orbits, then it follows that G is Goduchon if and only if G is Kähler. So let me just say that all of these conditions that I just mentioned are conditions that are studied in general on non-Kähler geometry because they are some sort of weaker condition than being Kähler. Okay, so and in general they are called special metrics, and in particular G is pluriclosed if the fundamental true form omega is DDC closed. G is said to be balanced if the fundamental form omega is co-closed, where here this star is nothing but the G adjoint of D. And finally, G is said to be Goduchon if the Lie form is co-closed. That is equivalent to say that the power m minus 1 of omega is DDC closed. Okay, so in general, these three conditions are very different, okay? But by means of this, so we prove with this theorem that for this special kind of matrix, all of this just reduces to the Kähler condition. And moreover, the Kähler conditions for such matrix are nothing but an easy ODE in terms of H and F. Okay, so all of these conditions reduce to this simple ODE, which in terms of H and F. So this is not surprising at all, because since this matrix, these manifolds are constructed in order to find examples of matrix with special curvature properties. Okay, this means that the geometry of these manifolds are very strict, because in general it's very hard to deal with the curvature. Okay, so this is not surprising that the geometry of such manifold is so simple that they do not admit any special metric that are non-Kähler. So, okay, the next step is that let's have a look at the Second-Chern-Einstein condition. So since these manifolds, since this metric on such manifolds are described by two functions, the Second-Chern-Einstein conditions reduces to a pair of ordinary differential equations, okay, which I wrote down here in the slides. So you have two pairs of ODEs in which appears this functions lambda, which is a given function which a posteriori will be the Chern-scalar curvature of your metric. Okay. So actually, this is very similar to the Einstein equation in cohomogeneity-one found by Berard Bergery for the Einstein metrics. And the first things that one can look is to understand whether one can find local solutions to these equations. So in this spirit, we prove the following result. So assume that you have a singular orbit, okay, corresponding to the value r equal to 0. Okay. So then you need to fix one parameter a, which is a positive real number, and one admissible function lambda. So here admissible means the following. So when you have these geometric objects, okay, on these manifolds, the strategy is to study these geometric objects on the regular part of the manifold, okay, because the regular part of the manifold is dense. The point is that in order to extend geometric objects over the singular orbits, you need to impose some conditions on the boundary. Okay, so here this admissible means that this function lambda is smooth and it satisfies some conditions on the boundary of the interval. These boundary conditions, which are in literature they are called smoothness conditions, are well understood for this family of manifolds, but here I decided not to write them down because, I mean, they're not really interesting. So you just need to know that there are some conditions at the boundary that you need to satisfy in order to extend smoothly the tensors over the singular orbits. So once you have...
But Francesco, for instance, I don't know, lambda positive is allowed?
So, yeah. So you can choose also lambda constant here in this local existence result. Yeah.
And if you choose constant, it could be positive, negative, or 0?
Yeah.
Oh,
so
okay.
Constant functions are admissible. Yeah.
Okay. Thank you.
So once you fix this a and lambda, okay, you can always find two functions f and h defined on some small interval 0 epsilon, such that this pair f and h solve the Second-Chern-Einstein equations. Okay, so the systems written above, and moreover, they determine a smooth Hermitian metric on the regular, let's say, on an open set inside the regular part of the manifold, which extends smoothly over the singular orbit. Moreover, the metric that you get have Chern-scala curvature precisely equal to the function that you fix at beginning. So this is like a local existence result for Second-Chern-Einstein metric with prescribed Chern-scala curvature. Okay, and basically the proof of this result follows the same argument used by Eschenburg and Bang in order to prove the local existence of Riemannian Einstein metrics in cohomogeneity-one. Okay, so basically the technique is the same.
So when you say solve, it's also at zero. I mean, on the right, you take limit, or just for positive r, the equations.
So so if you write, so the fact is that these equations are singular in zero, so they are not well defined for r equal to 0.
Ah, okay. Okay. Solve then is for any positive r.
Yeah, for any positive r. Yeah.
Okay. Thanks.
But actually the f and h extend to 0, so they do not blow up for r going to 0. So you can really find some smooth functions on the interval 0 epsilon with 0 closed, so yeah. with 0.
Great.
So the next step here is, okay, so we have the local existence result, but one would like to understand the existence of complete solutions to that system, okay? And this is the content of our third theorem, so about the existence of complete Second-Chern-Einstein metrics. Okay, so if the manifold X has no singular orbits, for example, the case of the Hopf manifolds, then it admits non-Kähler Second-Chern-Einstein metrics which are homogeneous. And the proof here is very easy, because actually you just need to take these constant functions f and h given by this formula, and these constant functions solve the Second-Chern-Einstein equations. Okay, so here we are very lucky. We can find explicit solutions in the case where there are no singular orbits. And of course, since these functions are homogeneous, the metric that you get, since these functions are constant, the metric that you get is homogeneous. So let's move to a more interesting case. So if you have the case of one singular orbit, so for example, the case of the tautological line bundle over the projective space, then these manifolds admit complete non-Kähler Second-Chern-Einstein metric of cohomogeneity-one. So here we prove that there exist complete metrics. And actually, the proof of this theorem goes as follows. So we use the same method applied by Berard Bergery for the Riemannian case. So the method is, so the idea is as follows. So you introduce an auxiliary function phi, okay, and then you try to find a smart ansatz for your functions f and h in terms of phi. So you plug this smart ansatz in order to reduce the problem to a single ODE in phi, and if you are lucky enough, this ODE that you get can be integrated, so that you obtain this phi, and then by means of this phi you obtain f and h. So in the end, what you remain to prove is that this f and h verify the smoothness conditions, because in order to extend smoothly over the singular orbits, you need some boundary conditions, as I said before. And basically, by applying this method, we succeed in proving the existence of complete Second-Chern-Einstein metrics in case of one singular orbit. The last case, so the compact case with two singular orbits, so it is different because here we prove that for those manifolds, they do not admit any metric of this kind. And they do not admit any metric of this kind because of the following facts. So basically, by means of theorem B, we know that any metric G constructed in this way is necessarily globally conformally Kähler. So they admit a conformal change to a Kähler metric. And then it comes the following fact that this is like the big difference between the Riemannian and the Hermitian setting, that the Second-Chern-Einstein condition is preserved by conformal changes. So it means that if you have a Second-Chern-Einstein metric, then all the metrics in the conformal class are Second-Chern-Einstein as well. Okay? So moreover, since Second-Chern-Einstein plus Kähler, so if a metric is Second-Chern-Einstein and Kähler, then it is Kähler-Einstein. The existence of a Second-Chern-Einstein metric here, which would imply the existence of a Kähler-Einstein metric. But since we already know that these manifolds do not admit any Kähler-Einstein metric, we can conclude that they do not admit any Second-Chern-Einstein metric as well. And here again, the fact is that the existence of Kähler-Einstein metric is obstructed because the automorphisms group it is proven by Matsushima that the automorphisms group of these manifolds are not reductive. Okay, so this is like the case of the page. This is precisely the same as the page example is in complex dimension 2. So here we didn't.
Francesco, in the last case,
yeah,
with one singular orbit,
yeah,
you also had that it was globally conformally Kähler.
Yes, but the point is that here in this case the manifold is non-compact. So the metric that you get with the conformal change in general is not complete.
Okay.
And the point is that actually in some easy case you can compute the conformal change, okay? And it is crystal clear that the metric that you get is not complete.
Okay. Yes,
yeah.
yes.
Yeah, in fact, in principle, we thought that with this method, one can also construct Kähler-Einstein metrics for spaces with one singular orbit, but actually it is not true because of this issue with the completeness. So, so this concludes the study of Second-Chern-Einstein condition for these metrics. And the last conditions that we studied is the so-called constant Cher.scala curvature condition. So by theorem C, if the manifolds have no singular orbits, we found Second-Chern-Einstein metrics which are homogeneous. So in particular, they have constant Cher.scala curvature. But the metrics that we constructed in the case of one singular orbits, they are just weakly Second-Chern-Einstein. So they don't have constant Cher.scala curvature. And in the case of two singular orbits, we didn't find any examples. So up to now, we did not show any constant Cher.scala curvature metric on manifolds which have singular orbits. So this is the reason why we decided to study these conditions. And basically, by using again the Berard Bergery method, we were able to prove this last theorem. Okay, so if you have a manifold X with one singular orbit, and if you fix a non-positive real constant, then you can always find a complete non-Kähler cohomogeneity-one metric with constant Cher.scala curvature equal to C. And the same is true in the case of two singular orbits, but in the case of two singular orbits, you need to choose C to be positive. So in the non-compact case, you need to choose C to be less or equal than 0, while in the positive case, you need to choose C to be positive. Okay. And also let me stress that this theorem B was known in a special case because the families of Berard Bergery manifolds with two singular orbits in complex dimension 2, they reduces to the family of Hirzebruch surfaces. And Koka and Leshmi proved some years ago that for Hirzebruch, so any Hirzebruch surface does admit a complete cohomogeneity-one metric with positive constant scalar curvature. So you can read this theorem as a generalization of their result in any dimension. And basically, this is all that I wanted to say. So if you have any questions, I don't know. Maybe I can. Okay, so I now can see you. Okay.
Is there any question for Francesco?
I have one, but I've been asking too much.
you
Okay.
Jorge.
No, but first somebody else. I don't know. Well, okay. Then, yeah, in where you find the homogeneous one,
Yeah.
it looks like a too long way to get the homogeneous one. The question is if these homogeneous were known, and if you know all the homogeneous, for instance, Second-Chern-Einstein on these spaces.
Okay, so yeah, it is true. It is a very long way to get something that maybe can be proved in a smarter way. But actually, the point is that we didn't. I mean, we didn't expect to find homogeneous solutions. So that's why we begin with the cohomogeneity-one approach. And so in general, to classify homogeneous solutions, you need to know the isotropy representation of the space, right? So let me go back to the.
But then your homogeneous solutions are new.
So yeah, as far as I know, they are new. As far as I know, they are new. Yeah.
Oh, okay.
So here, okay, it depends on the space that you started with. So for example, if you all of these spaces P are irreducible, and almost all the total space of this almost all G over H are again irreducible, but not all of them. So for example, if you start by taking P equal to SO K plus 2 over SO2 cross SOK, for example, in that case, the total space of the fibration is SOK plus 2 over SOK, and the isotropy representation of that space is it admits two equivalent segments.
Yeah.
So in that case, so there are other homogeneous metrics.
I see. Yeah.
But in general, so it seems to me that all of the other cases, at least excluding the two exceptional cases, they are irreducible as well. So the action of H is irreducible. So I think that you don't find any other metric.
Okay. So it's quite a surprise, this homogeneous metric, no?
Actually, so as far as I know, they are not known because I think that nobody write down the Second-Chern-Einstein equations for such spaces. So maybe that's the reason why they were not known.
Okay, thank you. No more questions.
Okay.
Is there any other question for Francesco? Well, if not, let's thank again Francesco.